I want to say a word about algebraic topology, because homology groups belongs to a domain of mathematics which is called algebraic topology, which is a theory where we try to use algebraic methods to do topology. And there are a lot of notions that algebraic topologists defined. So I wrote here 4 objects, but there exist many more. And what we are interested in persistent homology are the homology groups. This is a current theory of persistent homology and topological data analysis. But I have to say that some current developments of topological data analysis are interested in these other notions. So homology groups, there are several ways of seeing them, and we will define simply in this course the simplicial homology groups. It is a more natural way of seeing homology, and moreover, we will restrict to the case of simplicial homology over a finite field. And the finite field we will use is the most simple finite field, Z over 2Z, the field with 2 elements. So before defining homology groups, we have to do a little bit of algebra. So this lesson will start with a reminder about groups and vector spaces. So first, could you please tell me in the chat if you already know what is a group and what is a vector space? All right. Awesome. Seems like you are all already familiar with these notions. Okay. So this first part, I will just recap the usual definitions. Maybe vector spaces over finite field is something new for you. So do not hesitate to interrupt me. So we'll start with groups. So this is usual formal definition of a group. Let me just recall you that a group, G, is simply a set where you have defined an operation that I denote plus here, such that this operation satisfies 3 axioms. It has to be associative. You have to have a 0 element, an identity element, and every element of your group has to have an inverse. And we will have a particular look at the group of integers today. Z, the group of integers, is a group for the addition. Okay? And a convenient property of groups is commutativity. We say that a group is commutative if the order of the elements in the operation is not relevant. If for every 2 elements AB of your group, A plus B is the same as B plus A. Okay? The group of integers, of course, is commutative. 1 plus 2 is equal to 2 plus 1. Okay. We will also need quotient groups. first, I define a subgroup of a group. So I have a group G. I define a subgroup H as any subset of G, such that if you take two elements of H, then their sum, A plus B, is still in H. And this notion shows that the operation plus on the group G restricts to an operation on H. So a subgroup can be seen as a group. And if we take the example of the group of integers, for every natural number, for every integer p, you can define pz, the set of elements of the form p times n, where n is an integer, the set of multiples of p, and so this is a subgroup of z. I just have to prove this axiom. So I take two elements of pz. The first one could be pn and the other one pm. Their sum is p times n plus m. This is still an element of my subgroup. So pz is a subgroup. And once you have a subgroup, you can consider the quotient group. So the definition is here. All the groups we will consider will be commutative. Once you have a subgroup, you can define an equivalence relation on G as follows. Say that any two elements of G are equivalent if their difference belongs to the subgroup H. So you can show that this is an equivalence relation, and you can consider the quotient set, the set of equivalence classes. And you can show that an equivalence class for this relation has the form A plus H for some element A of G. Still an example with PZ. This definition in the context of the integers, we say that A is equivalent to B if A minus B is an element of PZ, which means that P divides A minus B. Okay? And I can have a look at the equivalence classes. If I take any A in Z, its equivalence class is a set of elements that are equivalent to A. So according to this thing, I know that the equivalence class of A is the set of integers B such that P divides A minus B. And you can see that this set is equal to A plus PZ, as we have here. And what happens is that this quotient set, the set of equivalence classes, can be given a group structure. I can write the quotient set as something like that. I choose a representative of each equivalence class. And now I define this operation plus on the quotient sets as follows. If I have two equivalence classes, AI plus H and AG plus H, I say that their sum is AI plus AG plus H. This is an equivalence class. You can show that this gives the quotient set a group structure, and we call this group the quotient group. And if we continue with our example, PZ for any integer p is a subgroup, and the quotient set consists in p elements. You can show that you have only p equivalence classes, and these classes can be written as pz, the equivalence class of 0, 1 plus pz, the equivalence class of 1, etc., until p minus 1 plus pz, the equivalence class of p minus 1. And to see it more simply, we can see z over pz as this set. I simply take the representative of each equivalence class. And now, the operation, the group operation on this set is simply the sum modulo p. So for instance, if I take p equals to 6, z over 6z, it has 6 elements, 0 to 5. And to find the sum of two elements, you simply compute their sum modulo 6. 5, oh, there is a mistake. 4 plus 5, this is 9, and 9 is 3 modulo 6. Okay. A quotient group that will be very important for us is the group z over 2z. So this is the exact same thing. We consider the subgroup 2z of z. We have only two equivalence classes. The first one is the equivalence class of 0. It is a set of even integers. And the second equivalence class is the equivalence class of 1. And it can be written 1 plus 2z, and this is the set of all odd integers. So my quotient group, z over 2z, it has only two elements, and the whole operation is given here. This is z over 2z. We will also need today the product of z over 2z. For any integer n, positive, I define the product of z over 2z by itself n times as the group with set being the Cartesian product, z over 2z times n. So this is a set of n tuples of z over 2z. An element of this product is a tuple of n elements of z over 2z. And the operation, the group operation on the product is given by this formula. You just sum the elements coordinate per coordinate. And yeah, also remark that z over 2z to the n is a set that has 2 to the n elements. Okay, this is it for quotient groups. Can you tell me in the chat if this is something new for you? Have you ever seen the group z over 2z before? Okay. Okay. Seems like it's new for some of you. So really take this, keep this in mind. Z over 2Z, this is the most simple group you can imagine. It has only two elements, 0 and 1, and the operation is given here. So this is it for groups. Now we'll talk about vector spaces. Again, I give you the definition, the usual definition of a vector space here. For a vector space, you need a field. I denote the field here F. So a field is a group with a multiplicative operation, okay? And you may already know the fields R and C. And a vector space over a field F is simply a group V plus. I use V instead of G so that we see that it's not only a group, it's even stronger, it's a vector space. So it's a group, V plus, with another operation that is called scalar multiplication. So you are allowed to multiply an element of the field and an element of the group together. And this operation has to satisfy 4 axioms. It has to be compatible with the plus operation on the initial group V. Right? Let's not read the axioms. Instead, I will talk about bases. So a very important notion in vector spaces theory is the notion of basis. Take any collection of elements of V, V1, Vm. We say that this collection is free if we have this formula. So this means that if I take any collection of elements of the field, and then I take the linear combination of my collection of elements of V with these coefficients, if this sum is 0, then it means that the coefficients already were 0. This is a free family. And this family is called, we say that the collection spans V. Yeah, Lucas, this is the definition of linear independence. Exactly. We say that the collection spans V, the whole vector space, if for any element of V, you can find a collection of coefficients in F such that our element of V is equal to the linear combination of my family here with the given coefficients. This is just a recap, a reminder about vector spaces. And when a collection is free and spans V, we say that it is a basis of the vector space V. Okay? And one of the most important statements is that if my vector space is finite, or more generally, if my vector space is finitely generated, then it has a basis. And moreover, all the bases have the same cardinal. They all have the same n. And this cardinal is called the dimension of the vector space. And Marcio says in the chat I think we have to add the requirement that the group V plus is commutative. Yeah. You, in the definition of a vector space, you ask the group V to be commutative. Exactly. But everything will be commutative today. All right. This is almost the end of the reminder. We now will define quotient vector spaces. Don't be afraid, this is exactly the same as quotient groups. First, we define a linear subspace of a vector space as a subset W that satisfies two conditions. First, just as for groups, we ask that the sum of two elements of W is an element of W, and that the product between any element of W and any scalar, any coefficient in the field, we ask that this product is still an element of W. And so this, we can show that if we have such a linear subspace, then the operations of the vector field V can be restricted to the subset W. So W can be seen as a vector field, a vector space on its own. And we can define on V an equivalence relation. So this is just as before. We say that A is equivalent to B if and only if A minus B is in W. You can define equivalence classes. You can consider the quotient set, and this quotient set can be given a vector space structure. You can define a plus operation and a dot operation. And this quotient vector space, I will write it V over W. And I would like you to keep in mind that there is a very simple relation between the dimension of the quotient and the dimensions of the initial vector spaces. The dimension of the quotient is simply the difference between the dimension of V, the initial vector space, and the dimension of the linear subspace. Okay. And at last, I define linear maps. A linear map between two vector spaces V and W is a map such that the image of the sum of two elements is equal to the sum of the image of the elements, and such that if you have the image of an element lambda V, where lambda is a coefficient, is equal to lambda times the image of V. Okay, this is very usual definitions. If such a linear map is a bijection, we say that the map is an isomorphism of vector spaces. And in this case, we say that the vector spaces V and W are isomorphic. And proposition here is that if a vector space has dimension n, if you can find a basis with n elements, then your vector space is isomorphic to the product vector space f to the n. So basically, when we talk about vector spaces, we are much more interested in the isomorphism class of vector spaces. What I mean is that if two vector spaces are isomorphic, they will be the same thing for me. So when I said that a vector space of dimension n is isomorphic to f to the n, it means that for me, f to the n is the only vector space that exists. If I understand f to the n, I understand all the vector spaces of dimension n. Okay. Oh yeah. A last thing, we won't consider, as you may have done before, vector spaces over the field R or C. We will consider vector spaces over the finite group Z over 2Z. So the before defining Z over 2Z vector spaces, I have to give Z over 2Z a field structure. And what I defined earlier here, I only give you the additive structure of Z over 2Z. But you can also define a multiplicative addition operation. This is really simple. You say that 0 times 0 is 0. 1 times 1 is 1. And 0 times 1 is 0. And this makes Z over 2Z a field. So if Z over 2Z is a field, we can consider vector spaces over Z over 2Z. And not all groups can be given a Z over 2Z vector space structure. What you can show is that a group V plus can be given a Z over 2Z vector space structure if and only if for every element of V, V plus V is 0. This is called, we say that each element of V has order 2. So I won't read the proof, but basically the theory of vector spaces over Z over 2Z is very simple. When your group satisfies this condition, then you can define a Z over 2Z vector space structure on it, and moreover, it is unique. And so this is interesting. If V is a Z over 2Z vector space, then it has cardinal 2 to the n for some n positive. And you can show that V has dimension n. And as a consequence, it is isomorphic as a vector space to the vector space Z over 2Z to the n. So I will add here that in this case, the dimension of V is equal to n. All right. So this is it for the reminder about algebra. I hope I didn't kill you. Okay. Yeah, everything is in the notes. I uploaded a new version of the notes yesterday. So from time to time, go on the web page and download the latest version of the notes. I give you the web page again in the chat. Oh, is it not? Oh yeah, sorry. There must have been a problem with the updates. I will update the notes this afternoon. Yeah. So okay. Let's continue. Yep. Excuse me, I have a little problem. All right. Now we can define homology at last. We will define homology for simplicial complexes. And I define here a useful notion that is called skeleton. Consider a simplicial complex, K. So for instance, here I drew this one. Remember that a simplicial complex simply is a collection of 0 simplices, the vertices, 1 simplices, the edges, 2 simplices, the triangles, and so on. For any integer positive n, I define the n skeleton of K as the set of simplices of K with dimension at most n. And I will also define here this thing, K n between parentheses, as the set of simplices with dimension exactly n. So this thing does not have any name, but it will be useful later. So for instance, the 0 skeleton, K0, is only the set of simplices of dimension at most 0. This is the set of vertices. And the set K n parentheses also is the set of vertices. The 1 skeleton, K1, is the set of vertices of simplices of dimension at most 1. So you have vertices and edges. Okay? K2, this is the same with also the 2 simplices. And we have here only 1 2 simplex, this purple triangle. What you can show is that for every n, the n skeleton of K is a simplicial complex, is a simplicial subcomplex of K. But Kn between parentheses, this guy is not a simplicial complex. As you can see, it does not satisfy the definition of a simplicial complex. Okay. And now, let me introduce to you the chains. Pick an integer, n. I define a n chain of k as a sum of simplices of k of dimension n with a coefficient in front, where the coefficient is an element of z over 2z. So remember that kn parenthesis is a set of simplices of dimension n. And the n chain is an abstract sum of n simplices times a coefficient between 0 or 1. Okay? Example, I will consider this simplicial complex k of dimension 1. You can draw it like that. So the zero chance is the set of sums over simplices of dimension 0. So it's a sum of vertices. And it turns out that we have 8 zero chains in this simplicial complex. For instance, the chain 0, this is when you take all the coefficients equal to 0. You have the chain that consists only in the vertex 0, the chain that consists only in the vertex 1, only in the vertex 2, and you can take also sums of these vertices. So you have the chain 0 plus 1, 0 plus 2, 1 plus 2, and you also have the chain that contains all the vertices, 0 plus 1 plus 2. Okay? The zero chains is an abstract set that contains linear combinations of the simplices. The one chains, this is a set of linear combinations of one simplices. We have two one simplices in this simplicial complex, the edge 1, 0 and the edge 2, 0. And my set of one chains contains 4 elements. When you take no edge, when you take simply 0, 1, when you take simply 0, 2, and when you take both. Okay. Now we are going to give the chains a vector space structure. First, we give Cn of k, the n chains, a group structure via the following formula. If you take two chains, then I say that their sum is this chain. Okay? I just add the coefficients, simplices by simplices. You can show that this makes Cn of k a commutative group. And moreover, we can give Cn of k a vector space structure over z over 2z. Remember that I told you before that a group can be given a z over 2z vector space structure if and only if, when you take any element of it, the sum of the element plus itself is 0. So I will prove that. let's get back to the chains. To prove that Cn of k can be given a 0 over 2z vector space structure, I take any chain of Cn of k, and I want to prove that the sum of this chain plus itself is 0. But by definition, this sum is equal to this chain, where I add every coordinate. And now, remember that epsilon, this is an element of z over 2z. And any element of z over 2z, when you add it to itself, is equal to 0. So this sum is equal to the sum, the linear combination with only zeros. So this is 0. Okay. So this is because 0 plus 0 is 0, and 1 plus 1 is 0. In z over 2z. So let me give you an example of the operation we defined on the chains. The sum, I take two zero chains, the chain vertex 0 plus vertex 1, and the chain vertex 0 plus vertex 2. Their sum, so this is associative, so I can remove the parentheses. Their sum is equal to 2 times the vertex 0 plus the vertex 1 and 2. And in z over 2z, the sum of an element by itself is 0. So these two zeros cancel, and I end up with only 1 and 2. Okay. This is a vector space structure we have on the chains. Now we'll define something else. Up. That is called the boundary operator. So follow me. Take any simplex of dimension n of k. A simplex of dimension n consists in n plus 1 vertices. This is an element of the n chains, and I will define its boundary as an element of Cn minus 1 of k as follows. The boundary of a simplex is the sum of all its faces of codimension 1. Take a simplex, look at all its faces of codimension 1, that is all the faces of dimension n minus 1. Take the sum of all the faces. This is a n minus 1 chain, and I call this chain the boundary of the simplex. So I define here the boundary on the simplices, but this can be extended as a map between on the set of chains as follows. If I take any element of the n chains, I define its boundary as the sum of the boundaries of its simplices. Okay? And we define like that a map between the n chains and the n minus 1 chains. And this is a linear map between vector spaces. An example, if I consider this simplicial complex, that can be drawn like that, the boundary of the edge 0, 1 is the chain 0 plus 1, because the edge 0, 1 has two faces of dimension 0, the vertex 0 and the vertex 1, and so by definition, its boundary is the sum of these vertices. Another example, consider the chain 0, 1 plus 1, 2 plus 2, 0. So this is a one chain, and I can consider its boundary. By definition, its boundary is the sum of the boundaries of all its simplices. The boundary of 0, 1 is 0 plus 1. Of 0, 2, oh yeah, I made a mistake. Thank you, Claudio. Here we should have 1, 2. One, 2, 0, 1, plus this should be a 1. Okay, plus 2 plus 2 plus 0. And as you can see, each vertex in this sum appears twice, appears 2 times. So you can cancel every vertex, and you end up with the chain 0. So the boundary of this chain is 0. All right, last example of dimension 2. I take the triangle, the simplex 0, 1, 2. It has 3 faces of codimension 1, the 3 edges, 0, 1, 1, 2, 2, 0. And the boundary of the triangle is the sum of the edges. Okay. So this is a boundary operator, or I should say the boundaries operators, because we have many boundary operators, one per dimension. Okay. And these operators satisfy very interesting statements. Take any chain of dimension n. If you consider the boundary of the chain, and then you consider the boundary of the boundary, then this is equal to 0. So composing 2 boundary operators give you the 0 map. So let us prove that. Oh yeah, I forgot something. The boundary operator on the 0 chains is defined as the 0 map. Let me write that somewhere. If n is 0, I define the boundary of any simplex as 0. Okay. Delta's the 0 boundary is a map from the 0 chains to the set 0, the set that only contains one element. All right, so let us prove that composing the operators give you the 0 map. If n was 1, then we will have delta 0 here. and delta 0 is by definition 0, so there is nothing to prove. I will suppose that n is greater than 1. So I want to prove that the boundary of any simplex is 0. If I can prove that, then by linearity, the boundary of any chain will be 0. So take a simplex of dimension n. I defined the boundary of sigma as the sum of all its faces of codimension 1. And I define the boundary of a chain as the chain of the boundaries of its simplices. So the boundary of the boundary is equal to the sum of boundaries of all the faces. And the boundary of a face is also the sum over all the faces of the face of codimension 1. Now I can rearrange the terms in this sum and say that it is equal to the boundary of the boundary. It is equal to the sum over all faces of codimension 2 of sigma with a coefficient here, alpha. And you can easily prove that this coefficient alpha is 2. Let me give you an example. If I take this simplex, the triangle 0, 1, 2, its boundary is the sum of its edges, and the boundary of the boundary, as we have seen, is 0, because each vertex appears twice. And you can show that each face of codimension 2 must appear twice in this sum. So this is why you obtain 0 at the end. Okay. So keep that in mind. This is a very important proposition. So let me recap what we have. We define for any n the vector space of n chains. And we have seen that these vector spaces are connected by boundary operators. Okay? These boundary operators are linear maps. And once we have a linear map, we can consider its kernel and its image. And this is what we will do. In any vector space of chains, I will define the cycles as the kernel of the boundary operator, and I will define the boundaries as the image of the boundary operator. Maybe I should write the definition here of kernel and image. Can you see when I write on my screen? Ah, nice. So the kernel is the set of chains C in Cn of k such that sorry. It is a set of C in Cn of k such that the boundary of C is equal to 0. Okay. And the image of the boundary operator is defined as follow. This is a set of boundary of C for each C in Cn plus 1 of K. Can you see the definition of the boundaries now? I wrote two equalities. Okay. I will use. Thank you. Okay, I will draw. The n boundaries. This is a set of boundaries of chains for every n plus 1 chain. Okay, I will write in the chat. Thank you for telling me. The n cycles, the n boundaries. This is a set of boundary of C. And the n cycles. And the n cycles is a set of chains, n chains, such that their boundary is 0. I just wrote in the chat. All right. I give you some examples here. We consider the same simplicial complex of dimension 2 with 4 vertices. And I say that we have... I have a question by Lucas. What's the intuition of the boundary being 0? This is a very important question. What is it? A cycle? What is it, an element of the cycles? You should see it as the boundary of a region, of an area in your simplicial complex. And we will see in a few slides that cycles will help us count the number of holes in our simplicial complex. But to understand that, you have to wait for a few slides. For the moment, notice that these 4 chains I wrote are cycles. So to prove that these chains are cycles, you just have to check whether their boundary is 0. And I give you here an example with this one. This is the same thing that before. The boundary of this chain is the sum of all the vertices where you see every vertex twice, and this is 0 at the end. Okay. And what are the boundaries? The boundaries are the images, the boundaries of simplices. So for instance, this chain here is a boundary because it is the boundary of the two simplex 0, 1, 2. Okay. Now, I define homologous chains. Take two chains. We say that they are homologous if you can find a boundary such that the first chain is equal to the second chain plus a boundary. Okay? And there is a very nice intuition for this idea. First, I give you two chains that are homologous. The chain 0, 2, 2, 3, 0, 3, this one, and the chain 0, 1, 1, 2, 2, 3, 0, 3. Okay? And they are homologous because if you take the second chain and you add this chain, which is the boundary of the two simplex, you have terms that cancel, and you end up with the first chain. Okay. So from our point of view, these two chains are homologous. So in other words, these two chains will be the same for us. Okay. And the important intuition is that you see this chain here, you can deform the chain to obtain the second one. This is what it means. Okay, if I draw a cycle, a chain, I can deform it by going through other simplices to obtain the other one. Okay. Now let me show you something. The cycles is a subset of the chain that contains the boundaries. Or in other words, the boundaries are included in the cycles. Or in other words, each boundary is a cycle. Okay? And this is very easy to prove because take a boundary, B. So by definition, B can be written as the boundary of a chain of an n+1 chain. Now remember that composing the boundary operators give you the map 0. So if I consider the boundary of B, this is the boundary of C, but the boundary of a boundary is 0. So the boundary of B is 0, which means that B is a cycle. Up. Okay, at last, now we can define homology groups. So, a recap. We have defined a sequence of vector spaces, the n chains, that are connected by linear maps. And in each of these spaces of chains, we defined the cycles and the boundaries. And we proved that the set of boundaries is a subset of the cycles. So the boundaries is a linear subspace of the cycles, and I can consider the quotient vector space. And this quotient vector space is called the homology group of K, the nth homology group of K. So this is the definition. The homology group is the quotient vector space of the cycles modulo the boundaries. And if we use the results of the first section of this lesson, we can say that the dimension of the homology group of order n is the dimension of the boundaries. No, this is a mistake. The dimension of the cycles minus the dimension of the boundaries. Marcio says, you can think of it as a geometric object without a border. You could walk inside it without ever getting to the border. Well, what are you referring to when you say that? Ah, okay. Thank you. We give another answer very soon. Okay. A vector space is totally described by its dimension. And this is what will be interesting for us. Let me define at last the Betti numbers of the simplicial complex. For every n, the nth Betti number of K is defined as the dimension of the nth homology group of K. No, Marcio, you can interrupt me. This is nice. Okay, this is the most important definition of today. And I hope it will make sense soon. So first, some examples. Same simplicial complex. I show you that the cycles, we have 4 cycles of dimension 1. You can find 4 one-chains such that their boundary is 0. And also, we only have 2 boundaries, the boundary 0 and the boundary of the 2 simplex. No, I gave you a lemma at the beginning. I will write it in the chat. If the vector space has cardinal 2 to the n, then it has dimension n. Because we consider vector spaces over z over 2z. So I can deduce that the cycles have dimension 2, the boundaries have dimension 1, and using this formula, I have that the dimension of the first homology group of K is 2 minus 1, and this is 1. Okay. And so, by definition, the first Betti number of K is 1. Kevin asks, why is Bn a subgroup of Zn? Why the boundaries is a subgroup of the cycles? This is what I just proved before here. The fact that each boundary is a cycle is a consequence of the fact that composing twice the boundaries operators give you the 0 map. Yeah, Thiago, right. This is a mistake here. This should be Z, and this should be B. All right. I want now to compute the 0th Betti number of this simplicial complex, K. So let us do that together. In order to compute its 0th Betti number, I have to find the dimension of its 0th homology group. And in order to find the dimension of its 0th homology group, I have to find the dimension of the 0 boundaries and the 0 cycles. And this is easy to do. I don't have many zero chains here because I have only 3 vertices. So at the end, I have only 8 different chains, and I can compute the boundary of each of these chains to see that only oh yeah, actually each zero chain is a cycle because I defined the boundary operators on the zero chains as the zero map. So the set of the cycles is very simple. It's the set of the zero chains. And I just forgot something. There should be also the chain 0. Okay. And what are the boundaries? In order to find the 0 boundaries, I take all the simplices of dimension 1 and I compute their boundary. I take all the chains and I compute their boundary, and what I obtain is the chain 0 and also the chain vertex 0 plus vertex 1 and also 1 plus 2 and 0 plus 2. And you can see here that the set of boundaries is a subset of the cycles. Okay. Now I count the number of elements in the cycles. I have 8 of them, so the dimension of the cycles is 3. And I count the number of elements in the boundaries. I have 4 of them, so the dimension of the boundaries is 2. And at the end, I can deduce the dimension of the 0th homology group. It has dimension 3 minus 2 equal to 1. Yep. And so, by definition, I have beta 0 equals to 1. What we will prove in the next lesson tomorrow is that beta 0, the 0th Betti number of a simplicial complex, is equal to the number of connected components of my simplicial complex. This will be a consequence of tomorrow's lesson. So when you will be used to compute homology, this exercise will only take you 1 second. You look at the simplicial complex, you see that it has 1 connected component, and so you can say that beta 0 is 1. Yeah. And that's how in the first tutorial I computed the number of connected components simply by taking the Betti numbers. Okay. I have a few words to say about homology groups of topological spaces. So what we did today is defining the homology groups for simplicial complexes. Okay. And we can also define homology groups for topological spaces as follows. Take a topological space, take a triangulation of your topological space, that is a simplicial complex that is homomorphic to your topological space, and say that the homology groups of your topological space are, by definition, the homology groups of its triangulation. Okay? This is the same idea that what we did for Euler characteristic last week. We said that the Euler characteristic of a topological space is the Euler characteristic of the triangulations of this topological space. When we say something like that, we have to make sure that the homology groups does not depend on the triangulation we choose of the topological space. Okay. Fortunately, this is true. If I take, well, I should say this differently. If I take a topological space and two different triangulations, then the homology groups of the triangulations are the same. The homology groups does not depend on the triangulations. And again, unfortunately, we won't be able to prove that in this summer course. But the usual way of proving this is by defining another kind of homology that is called a singular homology. Well, let us accept that we can define homology groups of topological spaces. We can also define their Betti numbers as the dimension of their homology groups. And last proposition of today, if I have homotopy equivalent topological spaces, then their homology groups are the same. And as a consequence, their Betti numbers are the same. So homology groups is an invariant of homotopy equivalence between topological spaces. All right, this is the last slide of today. Today we will learn how to compute these homology groups. For the moment, let me give you some examples. I take here the circle, the sphere, the bouquet of two circles connected, and two disjoint circles. So I say that the Betti numbers of these four topological spaces are 1, 1, 1, and 2. And as I said, we will see tomorrow that this corresponds to the number of connected components of our topological spaces. Their first Betti numbers are 1, 0, 2, and 2. And you can show that you can understand this first Betti number as the number of holes in your topological space. For instance, one circle has one hole. There is one hole inside the circle. Two circles have two holes, but a sphere does not have any hole inside. The sphere has something else. The sphere has a cavity. This is a two-dimensional hole. And you could say that Betty 2, the second Betty number, counts the number of cavities in our topological spaces. Okay, this is the end. So this was a really theoretical lesson. I defined homology groups, and we have seen that this is an invariant of homotopy equivalence. So we can use homology groups to understand topological spaces. And this is exactly what we will do in persistent homology and topological data analysis. Tomorrow, I will teach you the algorithm, the incremental algorithm that allows to compute homology groups. And we will be able to compute them on our own. So please have a look at the exercises 29 and 30 for tomorrow. And let me thank you very much.